Alright, so I'm doing the first tutorial second, I guess. This should be pretty quick because most of it's just like a first year review, at least for the first bit. But we have find the row-reduced echelon form of the matrix A. And how do we go about starting this? Well, we're going to need to know the elementary row operations. Because if we do not follow this, then we're going to get a system that is not consistent or equivalent. Right, because if we multiply an equation by 0, well, we're basically just nulling one of the elements of the system, like this. So for solving for something, we're not even going to be including this, assuming we multiply by 0 first. So the other one is adding a multiple of an equation to another equation. And I've shown this here. We can add r1 plus r2, r1 plus 2r2, any multiple, r1 plus negative 2 as well. You can do negative numbers. Then we have interchanging two equations, right? So I can swap row 1 with row 2, row 2 with row 1. I can just do that. You also have to make sure to not do multiple of these at once such that they override each other, right? Because that could also end up with inconsistent, non-equivalent solutions. Okay, but how do we start row reducing this? So I've highlighted in red what I like to start doing with. I like to look at the first column and try to get the pivots such that they're diagonally like this, right? So if I have a 0, 1 in the first column on the second row, I like to swap that up to the first row. Similarly, second, I like to just put that down here. So it follows this. So following from that, I look at the second row, the third row, I see that I can subtract multiples of the first to get rid of those. Then we end up with this, which is all multiples of 4 that are negative, so we can times it by negative to get rid of the negative. Divide by 4, then we get a 1 here that it's going to be our pivot. Then we see above and below it, we can also get rid of those. So we end up with this. Then we just have this alone on the third row, so we can multiply by negative to get it positive, divide by 2 to get a pivot. Then we see these two as well that we can get rid of, and that's basically it. So we just follow the elementary row operations to get to our row-reduced echelon form of the matrix A. What is the rank of A? So we define the rank of a matrix to be the number of pivots in the RREF of the matrix. So in this case, we have 1, 2, 3, right? We're just going to count. We have 0, 0, 0, 0, 0, 0. So these are pivots. That implies that rank of A is going to be 3. Give all basic variables of the system of linear equations AX equals 0, or X is equal to X1, X2, X3, X4. Transpose, so the transpose is going to look like this. We're talking about AX equals 0, so we're going to take our X, we're going to put it next to it like this. And basically what this is asking is to define our X1, X2, X3, X4 to be elements of the columns corresponding like this. So when we take AX equals 0, basically what we're going to do is we're going to find our solutions of X1, X2, X3, X4 with respect to their pivot or their column. So in this case, we see that X3, corresponding to column 3, is a free variable. Right, pivot 1, pivot 2, pivot 3, which is all we have, goes to X1, X2, X4, but not X3, so it's free. So what we usually like to do is we like to set these free variables equal to some parameter variable, which in this case we're going to do X3 equals t, and we're going to let t be an element of some field, right? It could be complex numbers, it could be real numbers, but since we have no defined field, we're just going to take element of some field. So the solutions for this is just going to be, we're going to set x1, x2, x3, x4, similar to how we find it up here. Going to set that equal to everything that we moved over, right? So if we go back to our original matrix, we see x1 minus x3 equals 0. Well, that implies that x1 is equal to t, right? Because x3 is equal to t. So we're going to move the x3 over here. It's going to be positive, so positive t. We look at our second row, we have x2 plus 2x3. Move that over, it's negative 2t. x3 is just free, so it's just t. And then x4 is just going to be equal to 0. Right? So then we take out our variable t here, and we end up with 1, negative 2, 1, 0. T is an element of f. That's about it. Since it asks for basic variables, I just went beyond that. You don't have to do what I just did. This is the full solutions. You can just give the variables that have the solutions, right? So, okay. Find all solutions of the following system. Right, so we're going to take this side over here, we're going to store it into a matrix like this, as I've drawn here. Then we're also going to take this side here, we're going to store it on the right side, divided by a line, so this is going to be our solution side, and this is just going to be our base matrix system. Once again, to find all the solutions, now we're going to RREF. So I noticed here that we have 1, 0, -2. We don't want that -2 there, so we're going to add row 1, well, row 3 from row 1, multiple of 2 to get rid of this. So we have 0 here. Once again, we have a pivot here. We want to get rid of this side and this side. So we're going to add multiple such to get rid of that. Then we end up with our REF, right? We cannot reduce this anymore. But since we have 0, 0, 0, 0, this is going to be a free variable, right? Because 0 is always equal to 0. So x3 is free once again. Let x3 equal t, some parameter, such that t is an element of f. Then we're going to take our solutions, final solutions. This is the one I did last time that you didn't have to do. So we have x1, x2, x3, right? Because x1, x2, x3, that's all of our variables, is equal to, and then we're going to solve this. So we have our base solution set over here, 7, 4, 0, 7, 4, 0 here. But then we also have -5, -1, and these are x3. We've defined that to be t. We're going to move that over. 7 plus 5t, 4 plus t, and t. Then we're going to take our t out, and then we're going to have our constant matrix over here to the right of it, just adding on for t elements on field. That's about it. I need to drink water. Find the determinant b of b equals this. So a lot of people weren't sure what to do here. Basically what we're going to do is we're going to do the crisscross method. So if you've never seen that before, basically what it is we're going to have some determinant m with a, b, c, d on top. We're going to take our a, we're going to go down right, like this. And then for our next variable b, we're going to go down left. C, we're going to go down right again. And d, we're going to go down left again, as I've demonstrated here. So it's going to be positive, negative, positive, negative, down right, down left, down right, down left, from one position, right? So down 1, right 1, and then if it's positive, you're going to go store them like this. If it's negative, you're going to store them like that. So this is generally how it looks like right here, right? A determinant of our box 1 minus b determinant box 1 plus c determinant box 2 red minus d determinant box 2 blue. So this is the pattern you're going to follow for all determinants, and you can do this for any size matrix. Very, very simple with n times n. Determinant of a 2 times 2 matrix is just defined up here. Right? A, B, C, D goes to AD minus BC. So we're going to use this fact for our next step. So following this step up here, we're going to do determinant B is equal to 3 determinant of our box over here, right? Down right, minus 0 down left. Because it's 0, we don't even have to include it, but I just wanted to do it to demonstrate this. Plus 4 determinant of our box again, once we're going to go down right, so it's going to be 2, 3, 0, 5. Then we're going to use this piece up here to find what the determinant of these boxes are, right? So A, B, C, D goes to AD minus BC using our crisscross method. So it's going to give us 3 times -1 minus 2 times 5. Here it's 2 times -1, but that's just 0, so we don't have to worry about that. Then here it's 2 times 5 minus 0 times 3. We don't need to worry about that. So then we end up with -39 plus 40 goes to 1. That's asking, is B invertible or not? So we have this little theory right here. If determinant m is not equal to 0, then m is invertible. Therefore, using this definition and our result above, we have B is invertible as 1 does not equal 0. And I provided a proof here of why, if the determinant is not equal to 0, then it's invertible. Right, so we have some n times n matrices. Suppose m is invertible and determinant m is equal to 0. Or we're going to show this. And there exists a matrix B such that B times M is equal to the identity matrix, and this is by the definition of invertibility. So then we have Bm equals the identity matrix, implies that the determinant of B times M equals the determinant of I, right? Because we can take the determinant of both sides, this is equivalent, which implies the determinant of B times the determinant of M. We can do this by the product of determinants is equal to 1, where the determinant of the identity matrix is 1. That's always going to be true. which implies the determinant of b times 0 equals 1, which implies 0 equals 1. Since we've arrived at a contradiction, as 0 does not equal 1, right, it cannot be the case that the determinant is equal to 0 if it's invertible. So then we go back to this definition and we arrive here. Right. This is the proof for that. So if you want to find what the inverse is, you can store the B matrix on the left side, the identity matrix on the right side, and then solve for the identity on the left side, and then you're going to end up with the inverse on the right side. Or you can just do 1 over the determinant of B times the adjacent of B. I need water. Hold on. All right. Well, let V be the first quadrant in XY plane. That is, let V equal this set here. Using the standard matrix addition and scalar multiplication to find out V, we can conclude that V is a vector space. So is this true or false? So we actually find that both of these are false, and I'm just going to go through it. So we're going to find that the scalar multiplication does not hold at all, because we have k times xy, that's going to be kx ky. But if xy is equal to 0, then kx ky is equal to 0, so that holds for all k elements on field. However, if xy is greater than 0, where we have k less than 0, that's going to end up with kx ky less than 0, which will not be an element of V defined up here where it's greater than or equal to 0. It's a product of multiples. So then we can find a counterexample to show that it does not hold for all xy element over V, so it's not closed under scalar multiplication. Right, so let xy equal 1, and k equal -1, and kxy equals -1, 1, equals -1, -1, which is not an element of V. So we say that it's not closed under scalar multiplication, and so V is not a vector space with standard matrix addition and scalar multiplication. Specifically, we looked at this. All right, then C, the set of S of matrices of form 3a plus b, 4a minus 5b, with the standard matrix addition and scalar multiplication is a vector space. So we're going to show that it contradicts, there's a 0 element that has 0 plus v equal v for all v. So let a b equal 0, then 3a plus b, 4a minus 5b is equal to this, which goes to 0, 4, 0, which is not equal to 0. So we say, therefore, 0 is not an element of our set S, and so S is not a vector space with standard matrix addition and scalar multiplication, as it contradicts this property. So then we have the last one. The set M2 times 3 R consists of all matrices of size 2 times 3 with entries in the field R. That M2 times 3 R is a vector space over R with the standard matrix addition and scalar multiplication. This is going to be true, right? So we define some standard M23R matrix right here with A, B, C, D, E, F over R. So we have A, B, C, D, E, F element of R. Follows all the properties for all vectors U, V, W element of our vector space, and scalars C, D element R. So I didn't run through the exact proof for this, but I just brought a pretty quick explanation for it. So we have V plus U as an element of V. This is absolutely going to be true because we can just imagine that we have VU matrices. Then all of our elements, right, like A1 plus A2 is going to be an element of R because we're adding an element of R to another element of R. So that's going to be an element of R. So it's closed under that. U plus V equals U plus V. Oh, U plus V equals V plus U. I didn't write that very well, but that's absolutely true, right? Because we're just going to have the standard matrix. A1 plus A2 equals A2 plus A1. Then U plus V plus W equals U plus V plus W. This is also true from the above reason. We can just show that, pretty simple. There exists 0 element V such that U plus 0 equals 0. So if we put in 0 for A, B, C, D, E, F, that's absolutely equal to 0. So there exists a 0 element. For all V element V, there exists negative U element V such that U plus negative U equals 0. This is the additive inverse. This is also true because we can have A, B, C, D, E, F all be positive. Those are all elements of R, so they're the element of our space. So then negative A, negative B, negative C, negative D, negative E, negative F is also an element of our space all over R. So this will also be equal to 0 if we add them together, and they're both elements. Then we have CV is an element of V. This is also true, right? If we define C and V sum for all of our elements within our matrix, multiplying them all by C where it's over R, is just going to end up with another thing at R. This is once again by the product of, well, just signs and fields. CU plus V equals CU plus CV. This is standard distribution. This follows here. Then C plus DU equals CU plus DU. Once again, this is standard distribution. We have this within our field. CDU equals CDU. This is just scalar multiplication, and this absolutely holds. And 1 times U equals U. Yes, so if we check all of these, this will all hold. I just didn't want to waste time with this, but I can show a more rigorous proof next time. But yeah. So yeah, I guess that was pretty fast. Once again, I can show all this if you want, but these are pretty brief explanations for why they work. Thank you. Yeah.